Hey there, it's Afiq, and in this video I want to talk about the math that I needed to learn to do a course in theoretical physics. Now, it is a truth and a fact that if you want to be successful in theoretical physics, or physics in general, maybe even engineering and computer science, you're going to need a lot of math. Now, one way to look at it is that a lot of people think this is quite unfortunate because there is a perception that math is hard. However, I view this as a plus because if you're learning math to become good at physics, you're actually killing two birds with one stone and learning a really important, beautiful, and valuable field alongside your physics. So I view this as a plus, and I wanted to make this video to sort of explain what kind of math you need for what types or subfields of theoretical physics you might want to study. Now, just for some context, it is indicative of how important math is by looking at what people did before they went and studied theoretical physics at a master's or PhD level. For one thing, lots and lots of people who go on to do theoretical physics did maths as their undergraduate degree, including myself. That's saying something. In addition, oftentimes theoretical physics departments are actually embedded in the math section of a university, or the math department of a university, and not the physics department. An example of this is the fact that in Cambridge, the Department of Math actually houses the Department of Applied Math and Theoretical Physics, not the physics department. So this is probably a good indication of how important math is. In addition, many famous physicists like Dirac, Einstein, and Feynman had really strong mathematical backgrounds. Alright, so without further ado, let's go into the type of math you need for different areas of theoretical physics. Now, the first area of physics that you'd probably learn in any theoretical physics course is mechanics. Mechanics is the science of how bodies move under classical physical equations and laws. For example, force equals mass times acceleration. Laws like the momentum of bodies in a closed system is conserved, and the momentum of energy in closed bodies is also conserved. In addition to this, you learn about conservation of angular momentum, inertia, and all of that stuff. So the reason why you need to know calculus is because calculus is the math of how variables change with respect to other variables and making deductions from there. So the reason why this is linked with mechanics is because, well, in mechanics, most problems are framed in a way that you only have a partial slice of information of how a system is. For example, how a system is at the very beginning, and you want to deduce how it changes throughout time and write down explicitly how those things change from the laws that you're given. Now, the easiest example of this is how a ball might roll down a hill. In a mechanics problem, you'll get the initial data, for example, where the ball is and how fast it's moving initially, and you want to deduce how it evolves. And hey ho, calculus is the study of how things change based on certain slices of data that the problem is given. Famously, calculus was discovered for physical problems by Newton when he tried to deduce the orbits of celestial bodies. Now, I understand that the hard part about mechanics is actually getting that physics problem and turning it into a math problem, but it does not hurt to have as many tools of calculus in your arsenal as possible, especially when you're dealing with complicated concepts in advanced mechanics. For example, many body problems where you have to deduce how maybe like 10 different balls might evolve in a certain physical situation. And also, surprisingly, it's useful to have a bit of philosophy, because you may ask, why do these conservation laws exist in the first place? For example, why should energy be conserved, or why momentum should be conserved? And there's actually very beautiful philosophical underpinnings of why these conservation laws exist. Right. So to learn mechanics from a very mathematical point of view, I would suggest the mechanics volume of Lev Landau's series on theoretical physics. that starts off with deriving the conservation laws from a very mathematical and philosophical standpoint. In addition, if you're more adventurous and want to look at electromagnetism, what's very important is multivariable calculus. This is the study of how multiple variables that are linked all together change under certain laws. And a lot of the electromagnetic laws in Maxwell's laws are formulated in terms of multivariable calculus operators. For example, the div operator or the cross product with div operator or the Laplace operator. So yeah, you'll need a lot of this, and I recommend that you study calculus from as many different sources as possible and do as many problems as you can. Alright, now let's go on to quantum mechanics. Now, in quantum mechanics, I personally think that the most important fields of math that you need to know are learning how to solve differential equations and linear algebra and complex analysis. So let's start off with the first one, differential equations. Differential equations are equations where certain quantities are related to other quantities based on how they change, or exclusively in terms of how they change. For example, Schrodinger's equation is a statement of how the wave function, which is the function that might describe how particles are distributed in space, change throughout time. And to come up with an explicit explanation of what this function actually looks like, you need to solve the differential equation, or you need to solve Schrodinger's equation. Now, to solve differential equations, you can use a variety of techniques, a lot of which include guessing, surprisingly, a lot of which include explicit ways to do things, and a lot of which includes Fourier transforms in linear algebra. But whatever method you use, it is an art in itself to understand which method is most appropriate for a certain situation. Surprisingly, group theory is also important because you can exploit symmetries to solve differential equations a lot easier. So yeah, this is why it's really important to learn a lot about differential equations before you study quantum mechanics. Linear algebra is also really important to study quantum mechanics because we describe a lot of the properties of quantum mechanical systems in a vector space. For example, the state of a particle is described as a vector, and this vector lives in a wider vector space called a Hilbert space. And so it's really important to understand key concepts in linear algebra. For example, how to get the eigenvalue of a matrix, or how to find eigenvectors, or knowing whether a space is, or knowing whether a matrix is diagonalizable, or looking at the range or domain of a matrix to understand quantum mechanics in a more non-superficial way. Now, in quantum mechanics, Hilbert spaces are the space of where states live, and they are complex spaces, which means that the numbers associated with these spaces include I, which is the square root of -1. And so having a grasp of complex analysis will easily allow you to navigate quantum mechanics more fluently and from a deeper perspective. Alright, let's move on to general relativity. So general relativity is currently the best theory that we have to describe gravity, especially gravity where there's lots of energy and lots of mass, like for example near a black hole, where things act weirdly. So to learn general relativity, the math you need the most is differential geometry. Now, differential geometry is a field of maths that uses a bunch of different things like calculus, multivariable calculus, to understand geometric properties of surfaces that are curved. And this is great because most things in the world are curved, like planets. So you want to study how little ants move around these curved spaces and what the curve means for how quickly they move around it. So things in differential geometry that you might need to know. Manifolds. So a manifold is a space where if you're an ant on the space, it looks like it's flat, like the Earth, for example, which is really important. Metrics, these are ways that you define distances on curved spaces. Curvature, and probably most importantly, geodesics, which are ways of finding the shortest path from one point to another on curved spaces. So understanding differential geometry is really important for the mathematical foundation of general relativity. And the good thing is that it's actually globally important. For example, neural nets and computer vision use differential geometry extensively in the more technical side of things. All right, now let's talk about particle physics. So particle physics concerns the smallest elements of matter. How these things are organized, the theory behind them, and how they interact with each other. So for example, what's a quark? What's a proton? What's a neutron? What are electrons? And what are the forces between them? Famously, one of the most important fields of math that you need for particle physics is group theory. Now, group theory is the science, or in abstract algebra, of how symmetries and transformations work together. For example, what are the symmetries that describe how a Rubik's Cube operates? What are the symmetries that describe what a triangle looks like? How can you map symmetries from one place to another, and how can you use them to solve problems? Now, the reason why symmetries are so important in particle physics is because in particle physics, most systems are defined by something called a Lagrangian. And the Lagrangian is basically an expression that encodes most of the data that we have about the state of the world. And in particle physics, this is very important. Now, these Lagrangians, somewhat magically, obey certain symmetries. And by symmetries, I mean that they look unchanged when you twist or transform the space in some way. For example, the most simplest example of a symmetry would be rotation. And most Lagrangians are invariant if you rotate the space and write down the Lagrangian again. Now, in the most famous model, and currently the most consensus and tested model that we have, the standard model of particle physics, is heavily based on symmetries. So for example, this group that defines the standard model is a function of several groups which have fancy names like U1, SU2, and SU3. And these form really a lot of the physical motivation for why the standard model is what it is. So by having a model where you guess the group or the symmetry set of the system correctly, you can then make predictions. And these predictions have famously given us predictions of the existence of different quarks. All right, now let's talk about probably the most important and most interesting field to me that you'll need. So quantum field theory. Now, briefly, quantum field theory is one step ahead of quantum mechanics and is what you get when you try to combine special relativity with quantum mechanics. Combining special relativity with quantum mechanics has given us explanations for loads of excellent physical phenomena. For example, particle creation, particle destruction, as well as the standard model itself and different types of interactions between particles. Now, the math that you need for this, unfortunately, is literally everything under the sun that I've mentioned. For example, you'll need a bit of group theory, you'll need a bit of differential equations, you'll need a bunch of stuff that actually mathematicians haven't really formalized yet. For example, the path integral is a technique to basically interpret how one electron might move from one state to another by averaging over the many possibilities that it could do that. And that is not actually a strictly mathematically rigorous thing to do. Well, in more than one dimension anyways. So yeah, you'll need to know as much as you can probability theory, other stuff like statistical mechanics, and analysis. Now, I hope this video has been somewhat helpful and has been a rough guide. Let me know if there's anything that you'd want me to explain further in this type of stuff, and I'll be happy to let you know you need to know. So yeah, like and subscribe if you want.